Okay. Quiz.
I know the answer was 355. I got 601. I did too. So I don't know how you got 355.
Well,
I got 601. But I got number 7.
let's see. Yeah, because there's two. There's
one was means.
Yeah.
Was, yeah.
And there's two different formulas for proportions. But let's see. Let's see what I get. I mean, I know what I did get.
Because you have a proportion right there, the 18%.
Right.
You get 601 if you don't use the 0.25.
I think that could be the thing.
You get like the 300 something.
Yeah. So, yeah.
I did the 2.5.
Well, that's right. So I think this one's one where you should use the prior info because this says that there was this previous survey that said that 18% access the state park. So they're going to do the survey again, but they want to reduce the margin of error this year. So if they think, so this is the key. So if they think that those previous surveys results were reliable, then they can use that p hat in their sample size calculation, and that's the difference. Yeah. So then the formula we would be using would be this one. Yeah. And you'll notice they are significantly different. Right, the numbers come out significantly different between what
355 and 601.
Yeah.
There's a greater margin.
Exactly. So that one's like the 0.25. That's the conservative one. That one's like overkill. Typically, you typically don't need that many samples. So that's why if you have the previous information, you kind of know where to expect the hat to be. You should use that formula because it's going to be a more accurate reflection of the.
Well, number 7.
Number.
Oh, I guess number 7 it doesn't matter. It's like one formula.
Yeah, number 7 is means anyways, and so then you're switching over to the mean formula. So that one you just have to recognize as averages. So you use the sample size calculation for averages, but you don't have to pick between two in that scenario once you recognize this as an average. So yeah.
For number 2.
Yeah.
On the calculator, I got 354.38.
That's true.
Why did you round it up to 355?
Because with sample size, what happens? Sample sizes you always round up.
Oh, so regardless if
Yeah.
the number next to it is lower than 5, it's going to be...
Yeah, always, yeah. That's why I included that last little line right here. Right, so rounding answers to the nearest whole number, and remember it's always better to sample from in than out of that. Because the key is always go that way. Okay. Yep. All right. Anything else from the quiz? Otherwise? No issues otherwise? Cool. All right. So we will go look at the stuff we left off on. And this is actually my notes from my other class, but I think this is where we left off, if I'm not mistaken. We were talking about type 1 and type 2 errors, true? Yeah. Okay. So we just looked at this. We're not actually going to do any, like, this isn't a class about criminal justice or anything, obviously, but the trial by jury example is a nice analog to help you understand how hypothesis tests are structured. Because the idea is there's a claim being made, you assume that claim is true until you can prove it, disprove it, or convince yourself that it's not true. But what happens is you can make errors. And again, this might look a little different than what we talked about yesterday. This is what this is my 150 section notes. But the idea is these types of errors, they work against each other. So you can't lower one without raising the other. So you can't convict innocent people less often without not convicting guilty people more often. But you can control the type 1 error, and that's the alpha level that you set. So like before I said you always pick your confidence level in advance. You always pick your alpha level for a hypothesis test in advance. And sometimes a type 1 error is worse, like in this case right here, we would probably, most of us consider probably type 1 is the worst of those two errors, right? We talked about this yesterday, right? Okay, shoot. I was like, wait a second. He was kind of looking at me like, you don't know what I'm talking about. But some, this we didn't talk about yesterday. This was in my own one. But see, the thing is that sometimes the errors are different. So the scenario I was describing to my other section was, if you think about like testing for diseases. So like especially communicable diseases, like for example, if you're designing a test for HIV, okay, well, if someone's coming in to get tested for a disease, the type 1 error is that you would declare them to have the disease when they don't. Okay, and the type 2 error would be that you declare them not to have the disease when they actually do. Right, so those are both errors you can make. Well, now in that case, though, which one's worse? A type 2 error is much worse, right? Telling someone they don't have the disease, like telling someone they don't have HIV when they actually do, that's a pretty big mistake. Whereas if you tell them that they have the disease when they don't, then what can happen? Why is that not as big a deal? So you say you have, go ahead.
Results can always come back negative.
Yeah, because they can always just retest, right? So if you tell someone they have the disease when they don't, that's typically what actually happens. If you get flagged positive for the disease, they have you retest. And they just retest you enough times to the point where you convince yourself that they do have it. But you really don't want to do this. And so sometimes a type 1 error is worse, but sometimes a type 2 error is worse. And that's why you pick different alpha levels. Because the alpha level controls your type 1 error rate. So if you say that I really don't want to commit a type 1 error, then maybe you would pick a really small alpha level. But if you say type 2 error is way worse, then you might actually raise your alpha level and accept more type 1 error and trade off for being able to not have as much type 2. Does that make sense? So it's kind of like they both are terrible. I mean, they both suck, but one maybe is better, preferable than the other. And so that's actually how we pick our alpha level typically when we're doing a hypothesis test or a confidence interval, based on which error we think is worse. Okay, anywho, so just a reminder about errors. This is the one we talked about yesterday. So we had a null hypothesis. The claim is that the truth is 45, and the alternative is we would be concerned about knowing whether or not the truth would be less than 45, right? So how would you commit a type 1 error in this scenario? What would it mean to commit a type 1 error in this hypothesis test? How do you commit a type 1 error? Right? You commit a type 1 error when you reject H naught, but the claim was actually true. That's a type 1 error. So in this case, what would you be deciding? Yeah. You're going to reject their claim, and you're going to decide that it's less than 45, but in reality, what's true? Yeah, so you're going to determine or decide that the truth is less than 45 miles per gallon when it actually is 45. Right. So in other words, you're going to go back and say, I don't believe you, Honda. I think you're telling a lie. I think the truth is actually less than 45 based on my sample, but in reality they were telling the truth the whole time, so that's kind of a bad look, right? But you could also go the other way, so then what's the other error you can make here? Yeah, so you would ultimately determine or decide that what? Yeah, so you would decide that the truth is 45 miles per gallon, but in reality it's actually less. Right, so you do that. So anyways, there's always two types of errors at play, and then you can decide which one of these you think is preferable or not. You know. So I don't know which one of these works. Is one of these really worse than the other in this scenario? What do you think?
Depends on if you're the manufacturer or the
Yeah, that's true. It depends on who you are. Because if you're like if you're say like a regulating agency like the EPA or something, which would you rather do? If you're the EPA, which would you rather do? Yeah, an EPA would probably err on this side because they really don't want to do this because it's their job to make sure that they're regulating the emissions or the efficiency correctly. So they would say that this is worse. Because even if you decide that it's 45 miles per gallon, but it's actually less, then you might say, well, okay, I could always go back and take more samples if I had to, you know, if they could come back and argue with me. But this one, or sorry, they would say, yeah, they would say this is better and this is worse, right? So here, this one is worse because if this happens, it's kind of like they're off the hook, right? Because if you say that it's 45, but it's actually less, once you declare 45, you're never going to go back and retest that. But if you commit this one, you could always go back and retest it. If that does that make sense? I think I said that backwards when I originally described it. Okay. All right. So this is what I was talking about before. The idea is that, you know, essentially these error types, they work against each other, right? So if you are trying to drive down your type 1 error, what you're going to do by consequence is you're going to drive up your type 2 error. And what we do is we pick an alpha level in order to control our type 1 error. So that alpha level is a probability of a type 1 error, but, and this is what we mentioned, that you can lower both error rates at the same time, but what do you have to do? And this is what we were talking about yesterday. What's that? More samples. Well, decreasing your confidence level is the same as raising your alpha level, right? So decreasing your confidence is raising your alpha level, allowing more type 1 error. So it's like, you can do that to lower your type 2 error, but you don't have to necessarily. You can lower them both at the same time if you take a larger sample size. You know, it's like more evidence. That's the way you can do it. So you decide what your type 1 error, what your alpha level is in advance. It's like, how much type 1 error am I willing to accept? And then your sample size is going to determine your likelihood of a type 2 error. And there's ways you could, like, there's something called power analysis in statistics where you actually decide how large your sample size should be in order to get your type 2 error rate down to a certain level. We're not going to do that, but it is something you can do. So for our sake, we'll just pick our alpha levels and perform the tests. We're not going to concern ourselves too much with type 2 error rates in this class, but they exist. Yeah.
So is there a way to quantify like the amount of bad that type 1 is versus type 2?
It's subjective, kind of, because it depends on the scenario and who you are, right? That's like kind of like what we're talking about. Is that what you're asking?
Yeah.
Yeah, yeah, I mean, you could do, yeah, I mean, there's people who specialize in like risk analysis, in which case they would actually probably quantify what it would cost. Like, okay, if I screw this up, what's it going to cost me? Because if I screw it up, it's going to cause this much damage, but if I screw it up the other way, I'm going to get sued and it's going to cost me this much money, you know, or whatever. So there is risk analysis that would actually somehow quantify those numbers. Yeah.
Where they want it to be.
Yeah, they could do that. And then you could say, well, then, you know, all right, well, type 1 is going to cost me this much, and type 2 is going to cost me that much. And so then you could kind of decide and make an educated decision about where you wanted those type error rates at. And you always have control over this. You always have control over this just by setting your alpha level in advance or your confidence level in advance. It's just that type 2 error that you have to, that's a little trickier. So, okay. All right, so now we say, okay, well, so we get the idea. You can frame a hypothesis test in terms of a null and alternative hypothesis, right? There's errors to consider. We can control some of them by the alpha level. We can control some of them with our sample size. But at the end of the day, you have to actually make a choice. And so the question is, how do you make the choice whether or not to believe the claim or not? All right. So here's another example. I don't think we talked about this one. Let's say that a professor claims 80% of students pass their course, but you think the truth might actually be less than 80%. So you're going to select 90 former students to test their claim. So if we were to formalize this, as a hypothesis test, are we talking about proportions or means? Yeah, this is a test about a percentage, or a claim about a percentage. So everything is in terms of P. What's the claim? Yep, the claim is 80%, but you think the truth is? Less than 80%. Okay. Now, question is, so this is their claim. Their claim is that the truth is 80%. Now, my question to you is, how far down the line would you have to go in order to no longer believe their claim? So, because you're going to go out and take a sample. You're going to get 90 people, and from that you're going to get some p hat, right, from those 90 people. So, if you talk to 90 people, I mean, what if your sample proportion was like 0.78? Would you still believe the claim? Still be reasonable? You know, but eventually, right, and this is kind of like what we were talking about yesterday with the Honda example, eventually if it got down to, let's say this isn't perfect, but I mean eventually, like if their p hat was like 50%, you're not going to believe the claim anymore, right? Because how on earth could they have an 80% pass rate and yet your sample of 90 people, only half of them pass? That seems pretty unbelievable at that point. Okay? And so what we have to do is we have to decide, what's that?
So you have a margin, but you go either way, right?
Yeah. So one way to perform a hypothesis test is you could actually just calculate a confidence interval and see if the confidence interval includes 80%. That's one way to do it. It turns out testing it like that will work, but only in only in a not equal to alternative when you care both ways, because the margin of error goes both ways. Like you were saying, it goes both ways. So we can actually discriminate a little bit better if we're doing a one-sided alternative because we only care one way. So we can still use a lot of the same concepts though, as we did when we constructed our confidence intervals. Okay. So this is what we got to do. We got to figure out how to decide where to cut this thing off. So here's the idea. So we know from the central limit theorem, right? It tells us that p hat comes from an approximately normal distribution. Right? It comes from approximately normal distribution centered around the true proportion. Okay. Right? And sometimes our p hat will be a little high, and sometimes our p hat will be a little low. But even if they were telling the truth, so even if this professor was telling the truth and the truth was actually 80%, just by random chance, sometimes we'll get p hats up here, sometimes we'll get p hats down there. Right? It just happens. So you could go out and you get a sample proportion, and I'll go out, I'll get a sample proportion, and we'll both get different answers, and they'll come from that normal distribution. Yeah? Okay. So then what we do is we say, all right, so since we know that if they were telling the truth, that we'd be drawing from a normal distribution, we can use the normal distribution to help us decide when to reject and not reject. Okay. So what we do is we say, okay, so once you set your alpha level, okay, now this is the thing about alpha levels. So a standard alpha level, just like a standard confidence interval is 95%, is typically 5%. That's kind of like the default. So most tests are set at an alpha 0.05 level. And if you want less type 1 error, you might lower that to maybe 1% or something. If you're okay with more type 1 error rate, you might raise it up to like 10%. But you pick that number in advance. So here's the idea. In our case, we need to come up, right? Let me use a different color here. Where's this? Let's say we know that eventually there has to be some cutoff, right? Because the claim is 80%, and eventually our p hats are going to get low enough to where we're going to reject their claim. Okay? So we have to come up with this cutoff somehow, and the question is, well, how do we come up with that cutoff? And it's all based on the alpha level. Okay? And the way it works is you think about, okay, well, what is a type 1 error? So alpha is the probability of committing a type 1, right? So what that is that's the probability that you reject the null hypothesis when the null hypothesis was actually true. Okay? Okay. Well then, if you work under the assumption that the null hypothesis is true, and then we're going to set a cutoff to where we're going to reject underneath it, then the way we do it is we just set that cutoff so that the probability of being outside of it or below it is whatever your alpha level is. So that's how you do it. So you say, okay, if I want an alpha level of say 0.05, and I'm doing a less than alternative, right? So I'm kind of got this cutoff. Then we can go find the Z-score. We could go find the Z-score, right, where 5% was below. Now the thing is this my, are those the Z-tables? Yeah, you got it. There's a pile of Z-tables over there, but I'm going to bring mine up. You could look this up on the table, but the table actually has a nice little, yeah, sort of. Yes, it's down at the bottom. There's a little cheat sheet for you at the bottom of the Z-table next to the confidence intervals. You'll see that they have hypothesis test critical values. Okay? And what it reads is it tells you the level of significance you want to use, so your alpha level. So these are the 3 most common alpha levels. That's why I don't even understand why they can include 98% confidence, because you never see it. And then they give you some cutoffs, but you'll notice the cutoffs have 3 columns. There's left-tailed, right-tailed, true-tailed. Okay, well, what does that mean? Anybody want to guess? Yeah, exactly. So this is when your alternative is less than. This is when your alternative is greater than. And this is when your alternative is not equal to, right? And actually, what do you notice? And this is why I was telling you about the not equal to alternative and the confidence intervals. What do you notice about the not equal to cutoffs? They're the same as the confidence interval values. Okay. Now, these are Z-scores. Like they're off the standard normal distribution. All right. So then that tells us that if we're going to perform a hypothesis test, the way we're going to perform a hypothesis test is we're actually going to perform it with Z-scores. So I think this one was what? Negative 1 point. If you go to 5% alpha level and it was left-tailed, what was it? Negative 1 point. Is it negative 1.645? Yeah. So that would be your cutoff. Now that's a Z-score. And then everything below that we would call the rejection region. Okay. So we care about, like in this case with the professor's claim, we care about finding out if the truth is lower than the claim. So we got to come up with a cutoff below their claim that we're going to make our decision at. The way we're going to do that is we're going to use a Z-score. And so what we do is we'll go get our sample and we'll calculate a Z-score from our sample. And then if the Z-score goes below our cutoff, then we're going to reject their claim. And then we can know that we retained our alpha level. And if the Z-score is above that, then we're not going to reject their claim. Okay. Okay, so we're working with Z-scores, but what does the Z-score actually look like? Well, we can just pull that straight from when we talked about the central limit theorem, right? The Z-score is just that. I did one little example with it, right? It's like the sample proportion minus the true proportion divided by, the square root, all that stuff. This all came from the central limit theorem. And what happens is the assumption is that we work under the null hypothesis And so we don't actually need to know the population proportion because we're working under the assumption that they're telling the truth. And so we can just use their claim as the true proportion for our test statistic. So I put a little p-zeros there because these p-zeros, these are the values that they're claiming is true. Right? And so this is your test statistic. Okay. So the p-hat, that's whatever comes off your sample after you go take your sample. Okay. And all of these p-zeros, so p0 is the claimed proportion. So then what we say is fine, I'll assume you're telling the truth. I'm going to go out and get a sample, and then I'm going to calculate a z-score based on my sample. And if what I see is so far away from what you claimed, then I'm going to reject what you claimed. In other words, if the z-score for my observation is like so far off from where you said it should be, then that's evidence that you're not telling the truth. So, okay. So this is how we're going to do it. It's a lot easier just to do it, though. So it's kind of like all these things. They're a little difficult to kind of justify, but they're not that hard to perform. Okay. So we could actually do one. Let's say this one we're talking about. All right. So let's say the claim is that the truth is 80%, but we're interested in determining whether or not we can show the truth is less than 80%. All right. So this is our setup. And then, so I'll always provide an alpha level for your hypothesis test, pretty much. So like on your quizzes and everything, I'll give you an alpha level to test it out. It'll have the alpha level on it. Okay. I think if you look at the practice test, I gave you the alpha level on all those as well. All right. So I want to know if you went out and you randomly selected those 90 former students and you found out that 68 of the 90 had passed, let's decide whether or not we should believe the claim. So in our example, first off, we need to calculate the sample proportion that we obtain. So what is the sample proportion from this output, or from this study? Yeah, it'll be whatever 68 out of 90 is. And so what does that come out to be? .7 6. Say we'll just round to 4 decimal places. There's no reason it has to be 4, but I just like to keep a couple around just so I'm not so good around here. Okay, so the claim is 80%, but out of our 90 people, 75% have passed. So it's lower than 80%, but the question is that low enough to justify going back and saying that we don't believe the claim, right? Okay, so here's the way you set these up. So the first thing we're going to do is we're going to find a critical value. We're going to find that critical value and establish our rejection region. So you're going to go, so this is a less than alternative, okay? So the less than alternative, that's telling us that we only care about rejecting to the left, and so this would be considered a left tail test. So our rejection region is only going to be in the left tail. Okay? So then you go to the table on your Z, you go to your Z table, and you look it up, and we actually just looked this one up, right? But if you look at the 5% left tail test, right? 5% left tail test, our cutoff would be a negative 1.645. Yeah? Okay, so then we say our test statistics can go all the way down to negative 1.645, but they can't go any lower than that. All right, and I'm just waiting to write that down. So then everything down here, this is our rejection region. Okay. And if our test statistic, if our z-score for our sample goes below that, we'll reject. If it doesn't, we won't. That's how we're going to make our choice. All right. So then you had to actually go get your test statistic. Now, this is only for proportions so far. We'll deal with means in a minute, but, well, maybe not today, but we'll deal with means. But the test statistic here is going to be that z-score. So the z-score is the sample proportion minus the claim all over the square root, all this stuff. So our sample proportion goes in for p hat, and then everywhere else we're going to be using their claim, because we're working under the assumption that they're telling the truth. Yeah. It's like, okay, fine. If you're telling the truth, and I took 9 samples, then my result would produce a z-score or whatever this comes out to be. I don't know what that is, so somebody's going to have to help me out on that one. I can try it on this computer, though. Negative 1.05? All right, let's see if somebody else gets that. Negative 1.05? Going once. Negative 1.05. I like it. Going twice. All right. Cool. So then this would be your test statistic. So what that means is, what it's saying is it's saying that our result would be 1.05 standard deviations below the expectation if the truth is that they actually pass 80%, right? So it's a measure of how likely our result would be under their claim, basically. That's what the test statistic is doing. And so it is below what we would expect, but it's not so far below what we would expect that we should be willing to deny the claim. And you can see up here, if you plot that, right, here's our cutoff, negative 1.645, and our test statistic doesn't make it into the rejection region, right? Okay. Our test statistic didn't cross that line. So it's below what they're claiming, but it's not far enough below that we should be ready to go reject the claim. Okay. Yeah.
It would have been negative 1 point. No, it would have been negative 1.6456 would be the rejection.
Yeah. If you hit that number, you reject. If you don't hit that number, you don't reject, no matter how close you are. And that's the reason you do that is you make a hard fast line so that you keep your alpha level. So that's why you make that decision. Yeah.
And this is like it's not exact, right? Like they could be playing at the top of the 95%, as long as yours isn't like way down there. Yeah. Like they could still be lying and confident that
exactly
you're close enough.
Exactly. And that's why we use the term fail to reject the claim rather than say accept the claim. Because technically, it's not like I'm endorsing this professor's claim. I'm just not able to disprove it. Okay. So here's the idea is, I need to put in one more slide here. Hold on.
But we don't actually know what the percentage that is, do we?
So what do you mean?
Like the negative 1.05.
Oh, you could go to the z-table and look it up, and you could actually figure out what the tail probability is. That's actually something called the p-value, which we will do. You don't need it though. You don't need it as long as you establish this cutoff, this critical value based on the alpha level. You don't need to go look up that probability to make your decision. But you could look it up, and it might give you some information.
Okay.
Yeah. So here's the idea: is since so if you looked at the cutoff negative 1.645, right? There's our rejection region. Our test statistic, negative 1.05. So then when you make that decision, okay, so typically decision should consist of two parts. The first part is that since the test statistic was not in the rejection region, then what should we do? Well, if it's not in the rejection region, then we shouldn't reject, right? Okay. So, because remember, the null hypothesis was that the truth is 80%. Our alternative hypothesis was that the truth is less than 80%. Our test statistic didn't make it into the rejection region. And really, so then that's the decision we're making, but that's gibberish to anybody who doesn't understand how to read this and how to interpret that. So you probably should go back and interpret that in a way that actually makes sense to people. What are you deciding? Right. So in other words, what are we basically determining? So I can't disprove the claim. So, well, what would you tell someone if they asked you, hey, is this person telling the truth? What would you say?
I'm not denying.
Yeah, as far as we can tell. You know? So there's a formal way that you can interpret these. So a really formal interpretation would be that there is not enough evidence to show that the truth is less than 80%. That would be a very, what's the word I'm looking for? A very, there's a word, but that's what a lawyer would say, you know. It's a very precise, yeah, diplomatic way or something. Yeah, it's a very precise or way to say this. I don't know how I can do it. Anyways, it doesn't matter. So what we normally do is we normally state our interpretation in terms of whether or not we could prove our alternative. So in this case, we say there's not enough evidence to go to switch to our alternative. There's not enough evidence that the truth is less than 80%. A less formal interpretation would be something like, you know, as far as we can tell, right, the truth may be 80%. I think the formal one might be a little easier just because it's very intense. Because if you fail to reject and say there's not enough evidence to show the truth is less than 80%, if you reject and you say there is enough evidence to show the truth is less than 80%. Yeah. So all you have to do is change whether or not there's not enough evidence or there is enough evidence. So as far as we can tell, it looks like the truth could be 80%. And the reason we say that, the reason that you frame it this way, there's not enough evidence, is there was some evidence that maybe that the truth is less. Because our sample proportion was below the claim. It just wasn't far enough below the claim for us to have enough evidence to reject. Okay? What do you think? All right. Yeah, quick as one. So basically, this is called a critical value approach to hypothesis testing. So the first thing you have to do is you have to get your critical value and your rejection region. Okay, and so the cutoffs. So the critical value comes from the z-table. Right, and it's based on your alpha level. And the rejection region is always the tails beyond the critical value. Okay. So now it actually depends on your alternative, because if you have, like in our case, we had a less than alternative. So we took, you know, our critical value was below. If you had a greater than alternative, you'll see the test statistics are positive. So your rejection region is above. But in a not equal to alternative, it's kind of a little different because you care both ways. And so that alpha level gets split in half. and your rejection region is actually two-sided. So that's why it's called a two-sided test, or a two-tailed test, because it has a two-sided rejection region. So I'm just going to put this kind of... Oops. Okay. But anyways, the point is you get the critical value off the z-table based on your alpha level, and the rejection region is always in the tails. All right. Hopefully that picture makes sense and isn't just chaos. But okay, then once you have your critical value, then you're going to go calculate your test statistic. But the test statistic is just that z value. And you use their claim as the proportion because you're working under the assumption that they're telling the truth until you can prove otherwise. Then you make your decision. So, and your decision is going to be either, right, if your test statistic, so if your test stat is in the rejection region, in other words, it goes beyond that critical value, you should reject. Okay. And then if the test statistic is not in the rejection region, then, well, you should reject. Okay. So you get your cutoff, you get your test statistic, you use those to make your decision, and then it's never a bad idea at the end to interpret that. And typically the interpretation says something like either there is or is not enough evidence in favor of the alternative. No. So it's normally in terms of the alternative. So, okay.
Is this what the quiz is on today?
No. So actually, the quiz is just up until, this is actually the next stuff. So 9.1 and 9.2 are all about setting up hypothesis tests and identifying type 1 and type 2 errors. So that's all the quiz today is. Actually performing the test is the second part of Module 9, the second part of that Chapter 9. That's the second quiz. Let's do next week. Yeah. Good question, though. So this part is going beyond what you'll get quizzed on today. But it will be on next week's quiz and the test. So, okay. All right? Let's do another one. Easiest way to get comfortable with it is just to do a few. Okay. All right. So here's a way that we use hypothesis. You can just read it, and then I'll talk about it in a second. A lot of information. So basically you have a situation where they'd like to know if the truth has gone below 25%. So they're going to do some surveys, and then they have to decide based on their survey output whether they should get rid of the muffins or not. Because in reality, you're never going to know for sure if the truth is, you're never going to know for sure exactly what the truth is. But if you have a threshold in mind, then you can test it against that. So how would you formalize this hypothesis test in terms of the null and alternative? And we're talking everything here, we're still working with proportions. So what we'll do, the way you can test something like this, you say, let's assume the truth is 25%, and then we'll determine if whether or not it's less than. So sometimes it's actually easier to start with the alternative, because the alternative is what you're interested in knowing, whether or not you can prove it. I'm interested in knowing if it's less than 25%, so I'll assume it is 25%, and then see if I can prove that it dips below that. Okay. Because that's kind of your threshold. That's your threshold. All right. Now, in their case, what was their sample proportion?
14 out of 100.
14 out of 100. Okay. All right. So that's 0.14. We'll need that. So then we can go ahead and get our critical value. Yeah, so we're going at the alpha 0.01 level. Yeah. And it's a left-tailed test like the last one. And so, yeah. Negative 2.33. So a few of you guys have found that, right? So you put your z table on the back side, and then this will be our cutoff. So our cutoff is going to be negative 2.33, and then everything below that is going to be our rejection region. Okay? All right, so you establish your critical value rejection region based on the alpha level and the alternative. Now what do we got to do? What's the next step? Yeah, take all of our information and go get a test statistic. Right, so it's that p hat minus p0. I'm just copying it down, but I'm about to fill in all the values. So our p hat was 14%. The claim is 25, so the 25% is where we're going to use for everything else. So it'll be 0.25 here, all over square root 0.25 times 1 minus 0.25 all over the sample size, which was 100 customers. And you get some z-score there. And I don't know what it comes out to be, but you tell me. I could try it out too here. No, I mean, you have to put it on your formula sheet. Yeah. But you do need to know it for sure, because you need to be able to calculate test statistic. All right. So what does that come out to be? Anybody get something? I got something. That's what I got. Yeah. All right. Yeah. So then, what we're saying is that if the truth were 25%, what we witnessed, 14% out of 100, that would be like 2.5 standard deviations below what we would expect to see, which is pretty far out. In fact, it goes past our critical value. And so what we see is, I'll just do it in a different color so it's a little clearer here, but our test statistic is out here, right? So in this scenario, then what should be our decision? Yeah, so then the test statistic is in the rejection region. You don't have to necessarily write this down, you know, like if you were on a test or something. You could just tell me, you know, what your decision is. So we should reject the claim because the test statistic is in the rejection region. Yeah?
Okay. So PO,
Yeah.
O, that's,
Always.
oh, it's just what P equals.
Yes. It's whatever the claim is.
Oh, okay.
Okay. So we'll reject claim, and then some of you guys already told me what it means, but how would you interpret that then? Yeah, so that's a very intuitive way to say it. So they shouldn't sell it because because 25% don't want it, right? That would be a completely acceptable answer. And so a formal one, a really formal interpretation would be there is enough evidence. Yeah, there's enough evidence to show that less than 25% want muffins. Okay. Or like you said, don't carry the muffins because 25% don't want them. So this comes off the z-table. So to get your rejection region, you go to the back side of your z-table where the cheat sheet's other side. Yeah. So they're down there at the bottom right table. So you look up the alpha level and the alternative. So it's a 0.01 alpha level with a left-tailed test. And so you can see right there, that's where the number comes from. Okay. Other questions about where any of these numbers came from? Okay? So then the idea is you can make a decision, you can justify it, and you can come up with that you can come up with that cutoff, and it doesn't have to be arbitrary. It's sort of arbitrary in the sense that it's based on your alpha level, which is something you choose. But once you set your alpha level, then the cutoff is fixed. It doesn't change. So that's why you always set your alpha level in advance. The standard's 5%, but you may see something lower than that or higher than that, depending on the particular experiment. Okay? Okay.
Is there a bigger chart if you wanted to go higher than that, other than what you show on screen? Not that you're gonna test this on the food, but if you want to do a 20,
you can look it up on the table. Well, you could just get it yourself, because if you wanted, like, if you really want, like, I don't really know exactly what the scenario would be where you'd have an alpha level that high, but say you did, and then it depends on your alternative. So, like, say you had a less than alternative, like we were working on, you just go to the Z table and find the 20th percentile. And then you get a negative Z-score off the Z table, just like we looked up percentiles before. You just go inside the table and look for the 20th percentile, and that would spit out your rejection region, if that makes sense. I don't know. I'm not looking at it. Yeah. And about which one's closest? Okay. Looks like maybe that one right there. Yeah. Negative 0. What's the Z-score? Negative 0.6 something. Yeah. Or negative 0. Negative 0.64. Yeah. So you can get that. So that would be your cutoff. That would be, and then your rejection region would be smaller than that. You typically don't see alpha levels that high, but could. Yeah.
It's probably because you're trying to minimize the outliers of it. So you've got a wider area that you're looking at.
Yeah, you could. It's just, what happens is just that if you let your alpha level get too high, then it's like, what's the point of even doing the experiment if you're admitting that you're going to make the wrong decision like 20, 30, 40% of the time, And so you get your alpha level high enough and it's kind of like, well, what's the point?
Then again, it depends on who is the benefit.
True.
If you're a construction worker and you want that
Yeah, maybe.
window.
Yeah, maybe. Yeah, it's possible. What actually we're going to do, and we don't have time, so I think it's probably a decent place to stop because we'll do one more example when we come back. Is there's something like you were talking is the p-value, and you can actually measure the probability beyond your test statistic, and that gives you a more quantitative measure of how strong your evidence is. It's like, is it really, am I really, really sure that they're lying, or am I just like, I'm kind of sure. So, all right, so that's why we'll come back on Monday. There is a quiz due today, but it's just over that first stuff, like setting up hypothesis tests and identifying type 1 and type 2 errors. So you should be okay with that.
How many quizzes get dropped?
One.
Oh my.
I dropped one quiz. But
Why did some of them then even though